Okay, so in this video, I wanted to make an example into how you can compute um, the power factor, the average power dissipated by a load, and also the capacitor that you need to connect to an AC circuit in order to correct the power factor. Okay, so for this exercise, we need to consider the following circuit. We have a voltage source of 120 volts RMS. And we have we know that the frequency of this voltage source is 60 Hertz. Okay. Also, according to the diagram, we can observe that we have an impedance of 10 plus J 12 ohms. Okay. This means that we have an inductive load. Okay. Because we have a positive sign for the imaginary part of the impedance. Okay. So based on the information, we can first conclude that we have an inductive load. Okay. We have an inductive load. And what else? Well, also you can see that based on this diagram, you can observe that these two elements are in parallel. Okay. So based on this information, we can say that the voltage of the impedance, okay, of this impedance should be equal to the voltage of the voltage source because the two elements are in parallel. Okay, so when you have two elements in parallel, we can conclude that the voltage is the same. Okay, and we want to compute what is the power factor of the circuit. Okay, also we can see that we have here the current. Okay, and the current, in fact, this will be an RMS current because we are working with an RMS voltage. The current of the circuit is the same for the source and for the load. Okay. And we need to compute first the power factor, okay? So we can use the complex power for this purpose, okay? But first, what you need to compute is the current, okay? But how can we use the complex power to compute the power factor? Well, you know that the complex power S is equal to the voltage in RMS, okay, and in phasor form, times the RMS current phasor, okay, but we need to consider here the conjugate. Okay, that is why I'm using an asterisk, no? To denote that we need to compute the conjugate of the current phasor times the phasor of the voltage. Okay, and also we can represent this as V RMS times I RMS. Okay, and the angle, okay, of the result of multiplying these two complex number is the phase angle of the voltage minus the phase angle of the current. Okay, and the reason of that is that when you are computing the conjugate of a polar complex number, basically means that you need to change the sign of the phase angle. Okay, so that is the reason I am placing this negative sign, because remember that when you have or you are multiplying two complex numbers in polar form, you can multiply the magnitudes and add together the angles. But since I am changing the sign of the angle for the current, I am writing here a negative sign, okay? Because of the conjugate that I am considering here. Also remember that the multiplication between the RMS voltage and the RMS current is the apparent power, okay? And also, this angle, okay, the result of subtracting the difference between the angle of the voltage and the angle of the current, and you compute the cosine of this phase angle difference, okay, is equal to the power factor, okay? Also, we can represent this complex power in rectangular form, and you will obtain a real part and an imaginary part. The real part that we call here P is the average power, okay? This is the average power that has units of watts, and Q is the reactive power that has units of volt ampere reactive, okay? Also, the units of the complex power are the volt ampere, the same as the apparent power, okay? And well, we have this information. What else we can compute? Well, we can also all use all the complex power to compute all of the metrics that we need, because we can use the complex power to compute the power factor, and also we can contain the average power by taking the real part of the complex power in rectangular form. Okay? The only problem is the value of the capacitor that we need to connect in parallel, no, to this circuit in order to correct the power factor. But let's first deal with the first 2 points. Okay? So based on this definition, we can in fact try to compute what is the complex power, okay? But first we need the current. We know the voltage, but we don't know the current of the circuit. So to do that, okay, to compute the current of the circuit, this is equal to the RMS voltage phasor divided by the impedance, okay? That is 10 plus J 12 ohms, okay? And this is equal, well, we know the value of the voltage, that is 120 with an angle of 0 degrees volts RMS divided by 10 plus J 12 ohms, okay? And the result of this operation is equal to 7.6822 with an angle of minus 50.90 1944 degrees amperes RMS. Okay, so this is the current. Now we can use the definition of the complex power, that is the one that I placed in this section. So we know that the voltage is 120 with an angle of 0 degrees volts RMS times the phasor of the RMS current, okay? But remember that in this part, we need to consider the conjugate of the current, okay? So this is 7.6822 with an angle of minus 50.1944 degrees. And you need to compute the conjugate of this. And if you multiply these two values, you will obtain the following, that the complex power is equal to 922.5865 with an angle of 50.1944 degrees, okay? And these are volt amperes, okay? So this is the complex power, okay? And if I compute the cosine of the complex power, of the angle of the complex power, no, this cosine is equal to the power factor, okay? So the power factor is equal to 0.64 018. And also remember that we can also represent this complex power in rectangular form. So this is 590.1944. Okay. No, sorry, this is 500 and 590.16 plus 780.19 J volt ampere. Okay, so the real part of the complex power in rectangular form is the real power. Okay, and the imaginary part is the reactive power. Okay, and well, we can plot this complex power in the complex plane. Okay, so you have a positive real power and also you have a positive reactive power. Okay, and what else? Well, this is the S value. And since here we are in the first quadrant, we can say that the complex power is lagging. Okay, So this is, and also we can conclude that this power factor is also lagging, and that is basically associated to the fact that here we have an inductive load, okay? So this is related to the characteristics of the circuit, no? The fact that we have a lagging power factor and the fact that the complex power is in the first quadrant of the complex plane means that we have an inductive load connected to the circuit, okay? So we have computed the power factor of the circuit is 0.64, and also we know the average power, that is basically the real part of the complex power of the circuit, okay? And what else we can do? So we can say that the average power, okay, the average power is equal to 590.16 watts. Okay, and this is the result of point B, and this is and the power factor is the result of point A. Now, once we have do that, we need to find the value of the capacitor, in order to correct the power factor of the circuit. Okay, so that means that we have here again the circuit. Here we have the voltage source, and here we have the load, okay, of the circuit, okay? And we need to connect a capacitor in parallel, okay, to the load in order to correct the power factor, okay? And in this case, we want to generate a power factor equal to 1 for the whole circuit. So what you need to do, or what we are basically doing in order to improve that power factor, okay, to move the power factor from 0.64 to 1, what you need to do is the following. Remember that we can plot the complex power in a Cartesian plane, okay? This is S1, and here we have an angle for this complex power that is theta 1. And the idea, well, we have here the reactive power, okay? And here we have the real power. And the idea of changing or improving the power factor is to move the complex power to this position. So that basically means that we want to reduce the reactive power, okay? We want to reduce the reactive power in order to move the complex power from the position of S1 to the position of S2. That means that we need to change the value of the imaginary part of the complex power, okay? We want to move the reactive power from Q1 to Q2. So we need to find a capacitor that produces a reactive power that counterweights the original reactive power labeled as Q1. Okay, we want the value of QC, that is basically the difference between Q1 minus Q2. Okay, we want to define the value of this, of the reactive power of the capacitor in a way that reduces the original reactive power that we have for the circuit and move it from S1 to position S2. Okay, so we also need to find the angle theta 2, that is the angle associated with the second complex power that we want to compute. Okay, so we know that this QC, okay, is basically the real part of the real power or the average power times the tangent of theta 1 minus the tangent of theta 2. Okay, so the idea is that we can compute the value of theta 1, okay? That is the value that we already have, no? Is this angle 50.1944 degrees, okay? And we want to find the value of theta 2. But the value of theta 2, that is the power factor, that is related to the power factor that we want, is equal to the inverse cosine of the power factor, okay? That in this case is 1, okay? And if you compute this, you will see that theta 2 should be equal to 0 degrees. That basically means that we are moving the complex power from the position of S1 to this position. In other words, we want to remove all of the reactive power of the circuit. That is the role of this capacitor, to subtract or to compensate all of the reactive power that we have. So we can use this formula, okay, to compute the reactive power that the capacitor needs to produce. So we know the real power, okay, that is 540.16, okay, watts times the tangent of theta 1, that is 50.1944 degrees, and minus the tangent of theta 2, that is 0 degrees. So we can say that the reactive power of the capacitor should be equal to 780.19 volt ampere reactive. Okay? And to find the value of the capacitor, you will need to take this reactive power, that is QC, and we need to divide this by omega times the square volt, the square value of the RMS voltage. Okay? So, well, in this case, the frequency needs to be expressed in radians over second, but we know that the frequency is expressed in hertz, and in fact, according to the original diagram, we know that the frequency of this voltage source is 60 degrees, 60 hertz, okay? So we need to convert this 60 hertz into radians over second, that is basically multiply the value by 2 pi. Okay, so we can substitute all of the information of the circuit into this expression to find the value of the capacitor. And this is equal to 780.19 volt ampere reactive divided by 60 hertz times 2 pi times the square value of the voltage, that in this case is, just one moment, 120. Okay, 120. And we need to square this value, and the result should be equal to 0.13045 millifarads. Okay, this is the result that you need to obtain, okay, by performing all of the computations. Okay, so this is basically the way in which you can compute all of the power information of a circuit using the complex power. And also you can compute power factor. And in fact, you can use the complex power to find the value of the capacitor that you need to add in parallel to your circuit in order to improve the power factor. Okay, so that's all for me. Thanks for your attention and see you later.